Okay. Okay, so this is work that I've done in collaboration with this is right with Nicolas Kovensky, and that should appear in a few days, hopefully. And also there's a little bit of earlier work done with Nicolas Ander Retolaza and Josip Pena. Okay, as Jose Barbon said this morning, we are here. It was the IPHT was built to be in the landscape, so I hope to stay in the landscape. So, oh, this doesn't work. Okay. Okay, so we mentioned scale separation, and let's start with just a few words. So DGKT is a prominent example of power law scale separation. So what is scale separation? Is that the Kaluza-Klein, the length of Kaluza-Klein is much smaller. So there's a large parameter, which is R, and the length, the Kaluza-Klein length is much smaller than the ADS length. So the mass, the Kaluza-Klein mass is much larger than the ADS, so one cannot truncate out the modes if such vacua exist with scale separation. Now KKLT is much worse, and here I'm going to talk about the supersymmetric ADS KKLT vacua. So with fluxes and Gaussian condensate. So forget about the anti-de Bruijn, forget about de Sitter. This is about anti-de Sitter supersymmetric ADS vacua. And this is an example, it's a prominent example where the scale separation is much worse or much better. So where these two scales are separated by this exponential behavior. Now, on the other hand, there's a Swampland conjecture that in the landscape, there should be no scale separation. So what's going on here? And well, you'll see. So also Severin, the next talk, will talk about his work where they show using ADS CFT that this ADS solution with scale separation is in the Swampland. So in this talk, I will tell you how this ADS KKLT vacuum is in 10 dimensions. What is exactly the internal geometry? What are the, what's everything? What are the fluxes? And so first, I will tell you what are the supersymmetry equations in the presence of Gaussian condensate, then a solution with smeared Gaussian condensate. Then we will talk about the localized solution, and this is work in progress, but actually this is too nice of a picture. The work in progress it's a little bit like that, so this solution has been very hard to obtain, and we're still in the process. And then I will discuss scale separation. Oh, I mean, before I start, a disclaimer. So this talk will be a little bit technical because this is technical, but hopefully the technicalities are understood, are clear, and if not, anyway, there should be a take-home message that should be clear. So don't worry if you don't follow the technicalities, you should be able to follow the take-home message. So the equations, so let's start with the equations first without Gaussian condensate. These things are general. So we have a work product metric of ADS with cosmological constant that is minus mu squared. So this parameter mu will appear. And again, it's the square root of the cosmological constant. And this is a maximally symmetric space. So we will turn on fluxes, which are only Lorentz invariant. So if they have a leg along space-time, then it's fully along space-time, or either they have an internal leg. And the NSNS flux is always it's internal. And because these fluxes are self-dual in 10 dimensions, these and these are related by this Hodge star in 6 dimensions. Now we are interested in supersymmetric solutions. And so there should be some supersymmetry spinors that are preserved, and starting from the 2 10-dimensional spinors, because we are interested in solutions in type 2, then you have n=1 solutions in type 2, they have a single parameter, a single spinor in 4 dimensions, and then a spinor in 2 spinors in 6 dimensions, and in general, these 2 spinors, they don't need to be parallel. So and we'll see whether they are parallel or not. Now this is you will see why this is tailor-made for the formalism of generalized complex geometry. And don't worry, I won't say too much about it, a little bit, but so instead of, in generalized complex geometry, instead of these two spinors, it's much nicer to work with the bilinears of the two spinors, which are forms. So they are just forms. And depending on the chirality of the relative chirality of these two spinors, you have only odd forms or even forms. So the one that is made of even forms, we call it psi plus, and the one that is made of all forms, we call it psi minus. And this encodes all the information about internal geometry. Well, all the information is encoded in the spinors or in this, actually in this, or it's much nicer to encode it in these bilinears of the spinors. So these bilinears of the spinors, so the simplest case is where the two spinors are parallel, eta 1 and eta 2, and they are depending on the phase, is depending of the kind of, so first if you do compactifications on Calabi-Yau, there's only a single globally defined spinor, which is on top is covariantly constant. But so the two spinors have to be the same, and they're the same up to a phase, and this is a phase which is which corresponds to O3 plane, which is a kind of supersymmetry that we're interested in. And in this case, then if you plug that in, what you get is that phi minus is just the the homomorphic 3 form of the Calabi-Yau, or of this SU3 structure manifold, and phi plus has a constant, plus a 2 form, plus a 4 form, plus a 6 form that you can write as e to the ij. Now, we will need, for the localized solution, what's called a local SU2 structure, which is when the two spinors are not parallel anymore, but they might be. So one way to parameterize it is by this angle. And then here there's one form that is, so this you can see the space, the 3-dimensional complex plane as separated between two directions, where we can define a holomorphic 2 form and a Kähler form. So these are called parallel, and this is a perpendicular direction where there is this one form, which is where the spinors, so the spinors have a part that is parallel and then a part that is sort of orthogonal, and this one form is this bilinear of the spinors. And why is that? So this structure will be relevant, and this may not be globally defined. So that's why it's not called SU2 structure. And this structure is relevant because we will have K-Shino condensation on these 7 branes. So it makes sense that the space is divided into some complex 2-dimensional plane, which will be parallel to the brane, and then something orthogonal to the brane. And then the pure spinors are much more complicated. So there's a mixture of J, parallel, omega, etc. So you don't need to remember all these details. It's just that they're more complicated than this. Okay, so in this paper with Alessandro, Michela Petrini, and Ruben Minassian from now a while ago, we found the supersymmetry, the ADS supersymmetry equations using this language of generalized complex geometry, and they look like this, and that's very nicely because, so these are the ones for type 2b, and if you want to do type 2a, you just replace psi minus and psi plus, and this is something like mirror symmetry. So there's a lot of things that one can say about this, but I won't say much more than that. The third one I wrote in parentheses because if you are in ADS, so remember mu is like the square root here. Mu square minus mu square is a cosmological constant. And if you're in ADS, if mu is not 0, this operator, which is d minus h wedge, is nilpotent. So d of this, dh of this is dh square of this. So this third equation is automatic when mu is not equal to 0. But since we will be sometimes close to the mu equals 0, so the small cosmological constant, so let me write it here. So again, there's a lot to say about this, but let me not say much more, except let's look at what the solution is with SU3 structure and O3 planes, where phi plus and phi minus are these. Now, if you look at the equation, so the first one is dh omega equals to this. So this tells you, since this starts from a 2 form, while here is a 4 form, this tells you that with this supersymmetry, with this type of supersymmetry, you cannot have ADS solutions. So the cosmological constant has to be 0. And then you get that you cannot have 0,3 flux, and then the omega is equal to 0. And if you keep playing with all the equations, yeah, let me not derive it, but it is very easy to see that you have dj equals 0, the omega equals 0, so it's a Calabi-Yau. So the first one says that it's Minkowski, these two say that it's Calabi-Yau, and then these 3 equations with the fluxes tell you that the G3 is imaginary, so this combination, this complex combination of Ramon and Neve-Schwarz is imaginary self-dual, and it has no 0,3 piece. So it's just 2,1 in terms of the this complex structure. Okay, so this much about the solutions with all 3 planes. So they are in Minkowski. Again, the flux is imaginary self-dual, and there is no 0,3 piece. And so this will be important later. So a very nice thing that we're going to use is that these ADS4 equations can be obtained from the effective theory. So this was shown by Kerber and Martucci, and then also by Casani, that if you write the n equals 1 chiral multiplets in terms of these pure spinors, so there is the chiral multiplets corresponding to complex structure moduli, which are the ones that descend in n equals to 2 from vector multiplets. These are just encoded in psi minus, so in SU3 this is omega, while the ones that descend from hypermultiplets are encoded in this combination of the Ramon potentials and the real part of this. And again, if we put that this is e to the ij, then you get j squared. And these are the moduli, the axion dilaton, and these are the moduli that one uses in KKLT, right? The C4 and then j squared with the dilaton. So if we call those moduli Z and T, then it's not hard to show, or it's not as straightforward as I show it here. The first one is that if you do, let me write what the superpotential is. The superpotential that was found by me and Lewis and Waldram, and then also Thomas. So the superpotential written in terms of these pure spinors, so these chiral fields, is written like this. And again, if you restrict to SU3 structure, you get the book of Bafawitten. So this is omega, and this is the combination of so the SNH, and here you will have a so maybe since how I put it here is not very obvious, but you get book of Bafawitten superpotential. Now with this superpotential, if you do the derivative with respect to the Kähler modulus, so this can pass here, and then this thing says that dz is equal to 0, and then the part, so that's a partial derivative, and then the derivative of the Kähler potential, which I didn't write here, that gives you this term. So these equations can be obtained. The second one is a bit more tricky because there is this star F, so it's not so straightforward, but one can show it, and Luca has shown it, that you get this equation. And these equations are, so you go in here from here using that mu is the vacuum expectation value of the superpotential with this e to the k/2, which again will be important. Okay, so now this is all for no Gaussian condensates. Now we want to add Gaussian condensates. So what is Gaussian condensate? So we have space-time field in DP branes in wrapping a P-3 calibrated cycle. Calibrated means that it's supersymmetric, some internal cycle. And these DP branes, so there's in general there's a non-abelian gauge theory, and there is Gaussian condensation. So there's a web for the Gaussian condensate given by lambda. And in particular here we're interested in these 7 branes wrapping a 4 cycle. So the equations, so these were the equations that I showed before without the Gaussian condensate. And with the Gaussian condensate, so actually it was Dimarsky and Martucci, the first one who thought about this and who proposed a generalization of this. And this is also discussed in this paper by Liam, Kachur, Kim, and Simet. And they were both almost there. It's just that there are different approximations that one does, and what we got are the equations, the general equations in pure blasted generalized complex geometry. So the first equation gets modified by this Gaussian and some delta function that has support on the cycle. And this is a two form, so delta 2 is a two form, which is dual to the four cycle. It's Poincaré dual to the four cycle. And we have this this expression. So this is for the 7 branes, but we wrote this expression for any DP brane, type 2A, type 2B, everything. And the second one, and this you can, well, I'll say it a little bit, the motivation. And the second one gets modified in this way, where here this is like a scalar delta, so it's a delta which has support in the four cycle, and it's such that it gives you, if you integrate this delta form, this scalar form over the whole manifold, it gives you the volume of the cycle. So that's a proposal for the equations, which again, it was mostly all in Dimarsky and Martucci, but they didn't have the cosmological constant, and now we added the cosmological constant. And then we also show that, so they propose this modification, and they propose it. This one is easy to see, but you have to be clever. They are clever people. So that if you remember this equation, one can obtain as the F term equation for the scalar moduli. Now, if you do the same, but including the non-perturbative superpotential, the non-perturbative superpotential is this KKLT thing, which is precisely given. So the moduli are these T moduli, so the real part of psi plus. Remember, this is J squared in the case of SU3 structure, and this is so the vacuum expectation value of this is the Gaussian condensate. So if you go through this, and since here you have a cycle, now you do the covariant derivative along T of the whole thing, and then it gives you the hint. It tells you what this modification should be. And the other is much more complicated because this superpotential doesn't depend on the complex structure moduli. But we show that indeed you can argue. So the way they argue was a little bit more indirect, but you can argue it this way. But now mu has to be the vacuum expectation value of the full W0 plus W non-perturbative for all this to work, for this thing here to work. Okay, so we have the modification of the equations for Gaussian condensates. And so now it's easy to see that if you put SU3 structure, the first equation is again DH omega. Here you have a two form. So that's why we said, so forget about the Gaussian condensate. If there is no Gaussian condensate, then you cannot have so the space has to be Minkowski. Now with the Gaussian condensate, maybe you can have, but look, this is a two form and this is a four form. So this equation is still, you won't be able to satisfy this equation if you don't have a one form piece, in here. So in psi minus, if you don't have a one form piece, then you cannot satisfy this equation. And again, this was noted by Martucci and Dimarsky. So you need to move away from SU3 structure. And if you want to solve this equation, you have to consider this local SU2 structure. So this is true unless we smear the source. So what does it mean smearing the source? This delta, I mean, we're all used to smearing the source, but it's thinking about smearing Gaussian condensates is a bit more weird, but it's not just more weird as smearing these 7 planes. So if we replace delta 2, and again, this was proposed by Korber and Martucci, so Luca has done a lot of work in here. So we should thank him for all this work. So if you smear the 7 brane, if you replace delta 2 by J, then you see now this equation, you can satisfy this equation without adding a one form, as long as mu is related to the vacuum expectation value of the Gaussian condensate. So in those cases, the equations, so these are the original equations, and here we replace this by J, and the factor is such that you get the volume of the fourth cycle either with this or with this. So this factor is dictated by by doing the right thing. And then this delta zero, we replace it by this, by just the, so sigma 4 is the volume of the 4th cycle divided by the total volume. And again, there's a reason why that's what we have to do. And then, so now the equation for the smear Gaugino, they look like this. And now the only way that this can be satisfied with this doesn't have a two form is if these two they cancel each other. So if the cosmological constant, if this parameter mu, which is the square root of the cosmological constant, is just directly the Gaugino condensate. Then the rest of the equations tell us that the omega is equal to 0, and that now H has a 0,3 piece, which is again proportional to mu. And the other equation here, the coefficients are such that precisely this term, oh sorry, well, anyway, let me write everything. Let me put everything. The coefficients are, let me go one step back. Let me put everything. So the coefficients here are just are precisely the laser and the things are close together. So the coefficients are precisely such that these two terms cancel, and so you get that the flux is still imaginary self-dual. So this together with this tells you is Calabi-Yau. And this says that the flux has no primitive component. So it looks very much like the solution we all know and love with the in Minkowski and 0 cosmological constant. So fluxes are self-dual. There's still a Calabi-Yau. The only difference is that you have now a 0,3 piece. Even if it's super symmetric, you have a 0,3 piece, which is proportional to the cosmological constant. And it's ADS. So this solution was Minkowski. This solution is ADS. So, but other than that, it's very, very similar to the cosmological constant. Okay, and so one thing, this mu, which is related to the Gaugino verb, it's so this is related. So this is W non-perturbative, but then at the same time, this mu with so lambda is related to the value of W non-perturbative, and at the same time we say the equations are consistent if mu is the verb is e to the k over 2 times this verb. So we get exactly the relation of KKLT, which is exactly the coefficient, which makes sense because we're smearing the Gaugino. So in a sense, we're looking at just the zero modes of this. So either KKLT is completely wrong, or the effective theory is completely wrong, or we are completely wrong. But if not, we get exactly KKLT. Okay, so let me not talk about the localized solution because it's still work in progress and it's complicated. So let me go to the recap before we get to scale separation, and I hope I have time. So yeah, let me put everything. So, okay, so we got the n=1 ADS solution with Gaugino condensates. We solved for smear D7 brane. The thermal space is Calabi-Yau, but there is a 0,3 piece and there's ADS, so there's a cosmological constant. And then we have the solution for localized D7, which is still work in progress. So now let's go to the scale separation, which, so we'll do this in the smear solution, though we think the localized solution behaves similar, and it looks like, yeah, that's the, and for a single Kähler modulus. So now all the geometric forms, they scale, so this scales like RQ, this scales like R square. The cosmological constant is related, so in our equations, it's related to the web of the Gaugino, so it has these scalings. The three-form flux has a piece, which is 2,1, that goes independently, and then this mu that scales like this. The tadpole tells us that, so this has to be order whatever of 100, but this can be satisfied, so this can be order of 100, and then this can be very small, and there's no problem with the tadpole. Now, the thing is what scales, what sets the scale of the Gaugino condensate, and that's the Gaugino condensate is W non-perturbative, and then so is given by this. But then our equation says that, or KKLT, that this is similar to W0. And so now if we look at scale separation, L Kaluza-Klein over L ADS, so L ADS is 1 over mu, and L Kaluza-Klein is 1 over R. So what we get is that this is some G string over RQ, and we get this exponential behavior. So the solution is scale separated exponentially, as long as you can build a vacuum that has a W0 much less than 1. And the conclusions, which let me just flash them. So the exponential scale separation depends on W0 much less than 1. We don't think the problem is in the localized solution, but I think the point is here. And then this W0 much less than 1 was attained in this construction of Liam et al. But this is challenged by Severin et al. And we will hear that in the next talk. Okay, stay tuned.
Thank you very much. Any question?
Yeah, very nice talk, René, very nice. A couple of years ago, I think Gary and other people, besides Liam, were also trying to do the KKLT in 10 dimensions. How does your work compare with them?
So yeah, there is this point about having lambda and lambda square, but I think you have a little bit of modification. So the modification that we have in our supersymmetry equation comes from a Gaussian mass term that they were considering, and they were considering the corrections of lambda to the 4. So it's the same kind of thing. Yeah, I don't know if Gary, you think. I mean, what's new is this smear Gaussian and showing that the solution is Calabi-Yau with imaginary self-dual fluxes, but now you have a 0.3 flux, which is proportional to the cosmological constant. That's the new part, and then, well, the localized solution that we are constructing.
Okay, so it's a different technique, but the results are great.
Yeah, yeah.
Okay. Thank you.
Yeah, Thomas.
There is this basic confusion about the localized case. So Gaussian condensation is an infrared effect, which essentially, I mean, you can think of it as the wave function for the fermions being very spread out, at least at large enough scales, at scales which are definitely higher than the Klein scale. So why is it insensible to think of the Gaussianos as completely localized within the extra dimensions? I don't know. To me, that's a confusion, but.
No, I mean, they are localized as much as the D7 brane is localized in that sense. So one can have the equation with this delta function, and far away from the source, they will look very much, I think the solution will look very much from the one we have. Yeah, I'm not sure if that answers your question.
We can talk about it. Over a coffee, maybe it's better.
Okay.
Thank you.
Maybe I can ask a question then. Regarding the unsmeared case, you had this delta function, but I couldn't see any warp factor on the left-hand side. But
yeah, sorry,
it should be there, right?
Sorry, yeah, I should have said that this. I put the dilaton to 0 and the warp factor, but there is so yeah, you can have a warp factor. So there should be you have to solve. So here is not the warp factor, but the one form that has to satisfy the D of E is a delta. But actually, Liam, well, no, but he constructed some solution localized for the D7 brane and has some of these things. So I don't think that's a problem. And there is a warp factor which is related to the dilaton, and yeah, we have some profile related to that.
Okay, maybe we have a minute for questions online. If there's no more question, then we can thank Mariana again.